Hey, welcome. Today we're going to be upgrading your calculus toolbox. We're diving into some of the most powerful properties of the Laplace transform. Now think of these less as just, dry formulas, and more like powerful shortcuts that are designed to make solving really complex problems a whole lot simpler. So let's get right into it. So let me ask you this. Are you getting a little tired of setting up that improper integral from 0 to infinity for every single problem? I mean, sure, it's the definition, and yeah, it gets the job done. But let's be real. It's slow, it's tedious, and there's a much smarter way to work. So that's what we're going to do right now. We're going to equip your calculus toolbox with 3 essential properties that are basically shortcuts. They're going to let you bypass all that heavy lifting of integration and start solving these complex transforms with some real elegance and speed. First up in our toolbox is the linearity rule. I kind of like to call this the divide and conquer tool because, well, that's exactly what it does. It lets you take a big, kind of intimidating problem and just break it down into smaller, much more manageable pieces. The core idea here is actually super intuitive because you've totally seen this before, right? Think about derivatives, integrals. If your function is a sum of a bunch of different terms, you can just tackle each piece one by one. And it makes perfect sense because remember, what is a Laplace transform at its core? It's just a fancy integral, and we all know integrals are linear. So here's what it looks like mathematically. The transform of a sum is simply the sum of the transforms. Now, I know, this looks super basic, right? But don't underestimate it. This is the absolute foundation. This property is why we can use a table of standard transforms for simple things like sine or t-squared to build up the solutions for way more complicated functions. Okay, on to our second tool, the first translation theorem. But honestly, pretty much everyone just calls it the shift rule. And this one is a total game changer, especially when you start solving differential equations. So what happens when you multiply your function by an exponential, like e to the at? It kind of sounds like it should make the problem harder, doesn't it? Well, the shift rule shows us something pretty amazing, that multiplication actually corresponds to a really simple operation in the s-domain, just a little horizontal shift. And if you think back to the integral definition, you can actually see why. That e to the at just combines with the e to the minus st to give you e to the power of minus sat. And what's that? It's just the heart of a brand new transform, where every s has been swapped out for an s minus a. It's built right into the math. And this right here, this is the whole idea in a nutshell. All you have to do is find the transform of your original function, f of t, which gives you capital F of s. Then you just go through that answer and replace every single s you see with s minus a. That's it. A multiplication in one world becomes a simple shift in the other. It's pretty cool. Okay, so why should you care? Why is this rule such a big deal? Well, it's because those exponential functions show up absolutely everywhere in physics and engineering. Things like damped oscillations in a spring or the response of an RLC circuit. The shift rule is the perfect tool for handling these exact kinds of real-world scenarios. Our third and final tool for today is the derivative rule. We just saw what happens when you multiply by an exponential. But what if you multiply your function by t? This is where things get really, really interesting. Okay, this one is super powerful and honestly a little weird when you first see it. A simple multiplication by t over in the time domain corresponds to the much more complex operation of taking a derivative over in the s domain. It's this kind of beautiful, almost strange symmetry between the two domains that gives the Laplace transform so much of its power. And here's the formal rule. If you multiply f of t by t to the n, what you do is you take the nth derivative of capital F of s, and then you just multiply that whole thing by minus 1 to the n. So for just t times f of t, you find one derivative of f of s, and you stick a negative sign out front. That's it. All right, our toolbox is officially upgraded. But theory's great, but let's actually get our hands dirty and put these tools to work. We're going to walk through 3 quick examples, one for each of our new rules. Okay, first up, a classic linearity problem. So step 1, just like we said, we divide and conquer. We use linearity to break it apart. Step 2, we just look up the individual transforms right from a standard table. And then finally, step 3, we put them all back together, do a little algebra, and bam, step 4, there's our answer. So simple, so elegant, and absolutely no integration needed. All right, on to the shift rule. For step 1, we identify our parts. The base function is cos of 3t, and that e to the 4t tells us our shift, a, is 4. So for step 2, we find the transform of just the cosine part. The key move here is in step 3. You just go through and replace every single s you see with s minus 4. which gives us our final answer.
And finally, let's put the derivative rule to the test. First, we identify our f of t as sine of kt. In step 2, we find its transform, f of s. Now for the really important part. In step 3, we have to differentiate that f of s with respect to s. And yeah, you're gonna need the chain rule for this one. And then we multiply the whole thing by -1. Notice the two negatives cancel out, leaving us with that clean final answer.
So there you go, 3 problems that would have been a real headache to solve with direct integration, and we just breezed through them using our new tools. Let's do a quick recap of our upgraded toolbox. Seriously, think of this slide as your new go-to guide. It's all about pattern recognition. When you see a sum of functions in the t-domain, that's your trigger to use linearity. You see a multiplication by an exponential, boom, that triggers the shift rule. And if you see a multiplication by t, that's your trigger for the derivative rule. All you have to do is recognize the trigger in the t-domain and you'll know exactly what action to take in the s-domain.
So that's it. You're no longer stuck with that slow, grinding integration. You've officially unlocked a faster, much more powerful way to solve these problems. So the real question is, as you look at your next problem set, which problem that used to look intimidating is now just an opportunity to use your new tools? Thanks for watching.